This video covers risk-neutral probabilities and discounting and compares it to actual probabilities. I teach a derivatives course, a financial engineering course that uses risk-neutral probabilities and discounting throughout. Most other courses you teach in business and a lot of business courses, even most finances courses, you're looking at actual probabilities, you're discounting with risk premiums built in. And so the risk-neutral probability stuff tends to be in the derivatives area, and it's not very well understood because it's a bit tricky. So what I hope to do in this video is show you just the intuition behind how this works and why the fact that we can use risk-neutral probabilities and discounting throughout a derivatives course without worrying so much that we're running into problems or we're inconsistent or scratching our heads. So why are we doing that? Why aren't we using actual probabilities? So if you recall, when we did in an options pricing context in a derivatives course, there's we do the binomial option pricing model, and the stock can go up, it can go up again, it can go down, it can go down and then up, it could go down and down. And so we went and figured out the probabilities of going up and going down in this context. And we determined that the probability of going up was equal to 1 plus the risk-free rate minus the amount it can go down here. So if we started at 100 and went down to 90, we would be going down about 10%, or it's about 90%. So that would be D, would be the 0.9, which would be 90% of 100. And then we could go up, and then we could go down, and the up would be, if this went to 110, this would be 110. This would be 1.10, 0.90. This would be 0.90. This would be 1 plus, let's say 2%. So we would get a risk-neutral probability in this context of 0.12 over 0.20. And so that would end up being, let's see, that would be a 60% probability of going up. That's what we covered in a binomial. And so we used a risk-free rate to calculate a risk-neutral probability. Now in the Black-Scholes model, we looked at the value of a call as being a stock price times ND of 1 minus the present value of the strike, which is this term right here, times the ND of 2. Now these two NDs are, the cumulative normal density function. They represent risk-neutral factors. Again, and remember, ND of 2 represented the probability that we would be paying this strike. So paying, see the minus sign, we'd be paying out this strike. It's an unconditional risk-neutral probability. And this was a risk-neutral probability with a couple of different, interpretations. But the interpretation for here is this was the probability that you would receive the stock. So there's an implicit positive sign with the call option. You would receive the stock conditional on it finishing in the money. So this was an unconditional probability. This was conditional. And so you see risk-neutral probabilities embedded in this Black-Scholes. And then not only that, but to be consistent, we had risk-neutral discounting, which is done here. That's what the R is. The R is a risk-free rate on a continuously compounded basis. Now the question is, how does this work? How does it compare to actual probability? And that's what I want to show you. Let's assume we have an economy in a world where the risk-free rate is 2%. We have a stock A. It's priced at $100 right now, and let's say we expect A to have a return of 12% over the next year. Okay, so that's the setup. So you can basically think of it as, look, we got a stock at 100, and it can go up or it can go down. Now let's put some numbers in about what can happen on the upside and the downside. So let's say the stock can go to 117 or the stock can go to 97. Just picking numbers out. Okay, which translates, so that's the price, which translates into a return of 17% and minus 3% in each situation. Now, let's figure out the actual probabilities associated with that. So the actual probabilities associated with this situation is, look, we got a 12% return, and we can go up at a rate P 17% plus 1 minus the probability, in other words, of going up, which is the probability going down, minus 3%. And what is P then? What is P? Oops, I should write this up here. What is P? Well, P turns out to be 0.75. Now that is a probability, an actual probability. I'm using the return that we expect to get, and I'm calculating probabilities that are consistent with that. Now we say actual because, look, this stock has an expected return of 12%, and this is what we actually think is going to happen. What we think can actually happen. Built into this expected return there was a 2% risk-free rate for the opportunity cost of money, plus there had to be a 10% risk premium to get to this expected return of 12%. Keep that in mind. Now, the probability, by the way, of going down would be 25% in actual probabilities. Okay, now, let's look at the same setup, but in a risk-neutral environment. So what we're going to say is, look, let's wring out the risk premium out of things. And we're going to wring out, so we're going to say, look, 2% equals the probability going up 17% plus 1 minus the probability going up, which is the down probability, times minus 3. And if we solve that P, we get a risk-free probability, risk-neutral probability of 0.25, and 1 minus is going to be 0.75. So what are these, and how does that work? I mean, we've got probabilities under two different situations. Well, what you see here is these are actuals, and this is risk neutral. The problem with doing everything on an actual basis is this risk premium, you can't see this risk premium, you can't observe it, and if you talk to about 100 people, they'd give you 100 different estimates for this risk premium. You can observe the 2% here, so this number is observed, this number is not, and so if this number is unobserved, then these actual probabilities are unobserved also, in a sense, unobserved, and are based on, the point is, they're based on this actual probability. But you can observe the risk-free rate. You go to the Wall Street Journal, you go to the web, and you find what a Treasury bill rate or 3-month T-bill rate is, and then you plug in what you expect to happen. What you end up with is you get risk-neutral probabilities that are consistent with a return that is risk-free. And so it works. So let's show you how it works. If you take, in this case, let's go right here for a second. If you take, let's discount the expectations here. The stock can go up 17%, right, to 117 with a 75% probability. It can go up 25%, or go down with a 25% probability to 97, right? And if we discount that back by the 12%, we end up getting a stock price of 100, which is exactly what we observe. So we can observe that stock price. Okay? Now let's look what happens when we do the same thing with risk-neutral probabilities and risk-neutral discounting. So we take the 25% probability of going up at 1 to 117, the 75% probability going down to 97, and we discount it by the 2% risk-free rate. And what do we get? We get 100, which is exactly observed. So what's cool about the risk-neutral adjustment is, look, if you have risk-neutral probabilities and you discounted the risk-free rate, you're going to come back to the same $100, the original price, as if whatever you decided to put in as an expected return. So you can put this in as 25%, calculate the probabilities, and you still come up with 100. So why not put everything in a risk-neutral sense, risk-free, and we can now discount everything at the risk-free rate and come back to all things that are observable. The 2% is observable, which implies these probabilities. It allows us to get to the actual stock price that we see. And so the point of risk-neutral pricing is you can apply this method to anything, and especially in the derivatives market, where we can't observe risk premiums, and different people have different risk premiums. So how do you actually model it? Well, we can model everything using the risk-neutral probabilities and risk-neutral discounting. And we can agree that it all backs down to the original observable price. So I hope this clears up risk-neutral probabilities and discounting.